Welcome to the second podcast for the Art of Engineering. This is the Bridge edition, and we are recording from the Transportation Research Board 95th Annual Meeting in Washington, D.C. I'm your host, Chad Harden with Michael Baker International, and I'm so happy and excited to welcome Dr. Mervyn Kowalsky, professor with the Department of Civil, Construction, and Environmental Engineering with North Carolina State University.
Thanks, Chad.
Thanks for agreeing to be on the show.
It's a pleasure.
The Art of Engineering is a podcast show where we explore the evolution of a career in engineering, and I also like to focus on the STEAM movement in terms of engineering outreach for schools, which is the science, technology, engineering, arts, and math, and where do those overlap, and where do those overlap with the people that I talk to. So just to tell you a little bit more, also I'm really excited that we're recording here at TRB. It's an annual meeting with transportation professionals from academia and engineers, practitioners, and also state DOTs, where we get to take the greatest, newest research and use that in our engineering in practice. So with that, I think we'll get started. And unfortunately, we had also invited Elmer Marks to be part of the show. With flights from Alaska, it was difficult to get everybody at the same time, but I hope to have Elmer on a future show. So back to Dr. Kowalsky. Mervyn, can I call you?
Sure,
Mervyn?
yes, please.
Okay. Dr. Kowalsky got his PhD from the University of California in San Diego, and he's the co-author of the Displacement-based Seismic Design of Structures, which is an excellent book for bridge engineers. I'm not new to bridge engineering, but still early on in my career, and I kind of see it as the update to the Priestley Bible that so many engineers or senior engineers in my office use. So I'm really excited that you're here. And now you're a professor with North Carolina State University. So will you tell us a little bit about your background?
Sure. Well, I went to school at UCSD, as you noted, and I actually was living in California at the time. My parents had moved to California before I started high school.
Okay.
So I was already in the area, and it was a great school, and was fortunate to be enrolled and to get into that school for my undergraduate degree, and enjoyed my time there immensely, and realized that wanting to pursue something beyond just a bachelor's degree, and that thought this was a great place to do so, and didn't really have any preconceived notion as to what within the area of structural engineering I was going to pursue at the time, but really towards the end of my undergraduate degree had managed to have some classes with Nigel Priestley, and that was just an eye-opening experience, I think, as for me as it is, I think, for any of the students that he's had in that over the past many decades. And realized that was a great place for earthquake engineering research. Was that this right place at the right time for me, and also all those earthquakes that happened during that time too. Right, that was a very active area in California.
Interesting. Now I understand UCSD is not, or at least currently not. If you pursue your doctorate or undergraduate there, in terms of structural engineering, it's not just civil and bridge engineering, but it's actually more of a whole approach to structural engineering. I mean, you could go and for people out there deciding to go to college, you could go and do aerospace structural design. Right. It's not focused like some schools might be really focused more on civil structural.
That's right. Yeah, I think it's the only program in the country that I'm aware of that is structural engineering. There's several architectural engineering programs, but that's not quite the same as just structural engineering. And they pursue, as you said, there's civil structures, aerospace structures, and I know it's branched out in the last decade to beyond just even that. But the strength was traditionally in the beginning more the mechanics-based, sort of civil structures and some aerospace. That's how it started. Okay. And then it's grown from there.
And I attended it was so wonderful. I was able to attend your workshop this morning on displacement-based design of structures. Direct displacement-based design. Sorry, direct.
The first word's important.
Yes, and I have to say, it's. I think one of the things about art is, and I talked a little bit about this on the last show. When you watch somebody who has just a whole career under their belt, so it's like watching a master in action. The way you explained the bridge design process with the direct displacement-based design, it looked easy, but I know that there was so much understanding that is going behind it. It's hard to articulate how much I appreciated that workshop. But
thank you.
I'm getting more into pushover analyses and things for bridges, and it seems like it's similar to a pushover analysis for a bridge, but kind of reordering the order of work in terms of that approach, and just a very rational and practical way, which was the other part I wanted to say, that all of the work that goes behind it, you've presented it in a way, and in the book, which I have, it's so practical and easy to implement. Not easy, but you framed it so easily to implement, I guess, and that's really hard to do.
Yeah. And I think a lot of that, the credit goes to Nigel, who I think had the vision to always to express things that appear to be very complicated in a way that's, as you pointed out, easy to understand. And a lot of us who've had the opportunity to work with them or learn from him have tried and do our best to do the same as he has in the past.
Well, I think you've succeeded, because like I said, I'm using your book as a reference for some of my current designs.
We have a reader. That's
yes, and I have to say it's excellent. And actually, I got introduced to that book through Elmer Marks here last year, and he presented simplified design methods with a lot of a basis on your work. So it just kind of coming together for me in terms of.
Well, Elmer's been very much a supporter of that, and I think he's gone through and really used that approach in some of his daily practice as a means of checking, for example, his designs he gets from other more traditional approaches. So it's neat to see people using it.
Yeah. Well, I wanted to ask you I sent you a couple of questions I was going to ask you.
Fair enough. So,
what do you enjoy in your area of work and research, and what is most challenging?
I was thinking a bit about this. I think there are a couple different levels to that. One, if you think about it just from the perspective of engineering research and education, just from that university perspective, and I think this is not unique to structural engineering, but certainly to most university environments, is that we get to work on a lot of different things. So it's never boring. So whether you're teaching a course, or you're working with your graduate students in the lab, or you're reading the latest research by some other colleague at a different university, or working on some committee, it's different and exciting every day. You never get bored. Even grading, if you don't can be interesting, right? If you make it that way. So that's nice from the perspective of just the educational research career. But I think more specifically, which is maybe what you were getting at in regards to the structural engineering research and earthquake engineering research, is that I find it fascinating, because you're really designing or dealing with the unknown loads. When you're dealing with earthquake engineering, unlike gravity load design or wind load, snow load, which are a bit more well defined, you really are designing a system for loads that you don't know, that you don't know what is going to happen in the future. And that makes it somewhat exciting, really. And then you couple that with a significant responsibility that comes with earthquake engineering as a practice. As you know, I mean, you have the public's welfare in your hands, especially in these high seismic regions. So that entire sort of picture, I think, is what to me is very interesting. I know that a lot of our graduate students who get involved in this, it really gets them excited about it, because they realize the impact of what they're doing. And
you're reminding me of something I was thinking about, is that why, again, back to the art of engineering, how is engineering an art? And for me, that is, we have so much a feeling of responsibility to do a good job, and also just a little bit of pride in our work, and that comes together. You put so much of your every day, so much of yourself into the work, that it's an expression of yourself in a sense, right?
Sure.
So it feels like a little bit of an art in that sense.
And it's, a lot of, I think, the civil and structural engineering fields, civil engineering especially, structural engineering being a part of that, is, it's very much a public service role. It's different from other realms of engineering. Your primary client, if you like, here is the public, and especially in bridge engineering, there. It's really is the very few privately owned bridges, right?
Right.
Not so many of those.
You mentioned the excitement that comes with the unknowns. It's funny, I was mentioning this podcast, which is my favorite podcast, is Star Talk with Neil deGrasse Tyson. And they had the last show, actually, oddly enough, was science and art. that was the subject.
Mm-hmm.
It's not always art related, so it was science and art. And one of the major conclusions to that was that art and science are related in that they both have constraints. And so what makes art exciting and what makes science exciting is that you have constraints, and so that is somewhat freeing, because then you can work within those restraints and come up with a new idea that might be out of the box but still meets the question or the demand for us, right?
Mm-hmm.
So that was funny.
That's an interesting parallel.
So maybe this is a little bit a similar question, but what aspects of your work require the most creativity or the least?
The least is probably the getting back to the grading bit. As an instructor, grading isn't usually too creative. It's
right.
It's probably the least creative aspect of what we do in terms of researchers and educators. But in terms of most, depends on a lot of the research that we're involved with. If it involves if it involves some experimental aspect of it, there's usually a lot of creativity that goes into making those sorts of physical setups work, where you're developing a model of your structural system that you're then going to subject to physical loadings, in this case seismic loading, and then getting all that to work together in a manner that represents as realistically as possible the actual system, and then measuring it, using the state-of-the-art instrumentation that you can find, and getting this to work. So going back over the last 10 or 15 years, that's always been some of the things that require the most, let's say, outside-the-box thinking, or being willing to do things different than what's been done in the past.
I imagine it takes a lot of creativity too. If you're going to model something in the lab, how do you simulate that? Because you can't always build a full-scale model.
That's right.
So how do you replicate something on a smaller scale?
Sure.
What materials can I use that aren't the same but similar? Right?
Yeah, certainly materials are an issue, and even if you can use similar materials, making sure that you're not altering the behavior by going to a smaller size. We try and do things at a scale that is as large as possible, and it's always fascinating to see when we have either students or their students with their parents coming in for an open house, coming into our lab, and they think someone who's not engaged in that, and they see lab, maybe they think, okay, there's a little desktop with a microscope. That's the labs that they're thinking about.
Right.
And you work into a structures lab, and it's several stories tall, as this enormous facility, and you've got these huge, structural elements, and it's not because we were trying to make things big unnecessarily, but because we want to address some of these issues of size and scale.
Right. Can you tell me more about your lab there at North Carolina State University?
Sure. We have the lab at NC State is called the Constructed Facilities Lab, or CFL for short. And it goes back to about 1996, just about 2 years before I arrived at NC State is when it was just open. So I had the opportunity to come to basically a new lab.
Okay.
And it's I think unique in the way in that not on the basis of any one piece of equipment, but it's a collection of things that can be done there. So we have the equipment such as an environmental chamber, for example. It allows us to do physical loadings of structures at very low or high temperatures, which is how we first interacted with Elmer Marks of Alaska DOT, was through our research to look at low temperature effects on bridges. So we looked at low temperature effects and what happens if you have an earthquake in the middle of winter in Alaska where it gets very cold. So we have a unique facility for that. And also a small shake table. We have numerous actuators, strong wall, strong floor, and an interesting geotechnical pit, which allows us to do soil structure interaction research. So none of these things by themselves are huge, but when you collect them all together in the one place, it is quite neat. And we have some interesting instrumentation systems that we've been using recently to do non-contact measurement of deformation. For example, on a bridge column, we traditionally may use strain gauges or other devices to measure deformations, and now we're using a non-contact system to measure strains on reinforcing steel, for example. So it really gives us some unique information that hasn't been available in the past.
Now, is that with a regular camera or like an infrared camera? Or how does
it uses the approach that we use utilizes infrared light, and we call these sensors cameras, but they're not so much cameras as they are these they are optical, of course, but they're measuring infrared light that's being emitted from targets that we've then placed on the specimen. So there's a couple different manufacturers for this type of equipment, and we've been using one from a firm out of Canada that's been working really well for us, and we've now got 3 such systems, and we're able to imagine taking something like a bridge column and then having these sensors all around it to get an entire 3D visualization of the entire space that you can monitor while you're loading it. So you can, as it's deforming, you can see the 3D representation on a computer screen, and you can then take that high resolution data and collect information that previously we've not been able to get.
Interesting. That sounds really exciting.
Yeah, it's a neat piece of equipment.
Let's see. I was going to ask, what is your favorite work of art or type of art in your own life?
It's an interesting question as well. Personally, I've got varied interests, but they tend to, it's kind of funny because they tend to be more, the word is maybe harmonic in nature, so I'm not so much of an abstract person, but I think that probably comes from the engine, as you know, engineers are very methodical in their thinking. We sometimes struggle with things that are outside our comfort zone, so when if I'm listening to classical music, I like things that that are really more from a different era, so not so much the modern music, or if it's the same thing with art, I like the landscapes and not so much the abstract things, but that's just the nature of, I think, a lot of people who are engineers seem to have some of those similarities.
How do you think your thinking or maybe problem solving has changed over the years from when you were a student to now?
I don't know so much if it's a problem solving or perhaps thinking of the bigger picture, which I think helps a bit. I mean, as a graduate student, we're so focused on what we're doing and we don't worry about so much of anything else, which is really probably how it should be at the beginning.
Right.
And you fail to see maybe the broader implications of what the research that you're working on.
Right.
So as time goes on, you get maybe a better sense for that. But even at the end of the day, we're still very much in the weeds of what we're doing. We're so close, so focused on something. You have to force yourself to take a step back and understand how everything fits.
Okay.
So I think that's something that's progressed over time, and it's nice to be able to apply that to problem solving. So that when you go through and you're trying to solve a particular research question, that you think not about just that particular issue, but how does that relate to the broader issue of the design of a structure? So, for example, if you're looking at the strains in the reinforcing steel on a concrete bridge column, something very, very, very precise. What does that mean in terms of you take a few steps back? And so how do you relate that to what would happen if there's an earthquake, to how long that bridge is going to be out of service, such that the people that live on the other side of that bridge can get to work or whatever it may be. So at least understanding the implications of that helps a little bit.
That's interesting. Yeah, that's a good advice. Just to when you're I think we all do this when you're deep in the trenches, even on the design side. Sometimes you feel like you don't have a chance to step back and kind of look at the whole picture sometimes. So.
Yeah.
Let's see. I have a couple questions from. So this is new this time. As our second episode.
Pilot study.
I wanted to do questions with Ask an Engineer. So these are questions that people sent me my request.
Oh, wow.
And so
good.
We can take turns answering them, or if you
you answer all the hard ones. So.
Okay. No. So this first one comes from Clint Isa, who's a geotechnical engineer at Diaz-Yorman Associates in Santa Ana, and actually he was my guest last time. And he said, what is your favorite bridge from an artistic perspective and why?
Favorite bridge? Well, I'm sure there's probably several that I'm not going to be aware of that I'm going to be missing out on. So in terms of the ones that I at least know a little bit about, there's a couple that come to mind, and I used to teach a bridge design course at NC State, and it was at an undergraduate level, sort of like a senior project class, and I taught that from like 2003 to 2010 or so. And there's several aspects of that course that involve bridge, design of a pedestrian bridge, and design of a proper DOT sort of highway bridge, but also had some conceptual design issues.
Okay.
And when we were going through that conceptual design issues, we used a lot of examples coming from more signature bridges, and one being the Millau Viaduct in France, which to me is just a very elegant structure in a very an environment that's it's complex in terms of the length that it's spanning, the height that it's crossing over, And aesthetically, it's just a very pretty bridge.
So I'm not super familiar with this, or I'm not familiar with this bridge. Can you, what aspect ratio wise, what's the length, the rough order magnitude?
Oh, gee. It was the main span is probably not huge in terms of modern cable stayed bridges, in the order of I would say probably half a mile or so, or something like this. So it's a pretty sizable in that regard, but it's the series of spans put together is crossing over a valley whose length is measured in many kilometers.
Oh, wow.
And the purpose for that bridge was that prior to that bridge, to get from one side of the valley to the other, you'd have to traverse through, back country roads. And my understanding was that it would take potentially hours to get from point A to point B, or something that couldn't take that long. And with this bridge, which basically crosses right over the valley, and it's the transit time is much shorter. Yeah. But it's done in such a way that if you've not seen photos of it, when you have the chance to take a look at it, it's just a really interesting, almost bridge. It almost appears floating in the right sort of light and the right environment. Oh, wow. So that's one that comes to mind. And another one that's much closer to home is Linco Viaduct, which is not an unusual bridge, but it's one of the early precast bridges in the U.S. and it was built in the mountains of North Carolina. And it's famous for it appears in many sort of advertisements for cars and so on. It's in very many movies. It kind of hugs the side of the mountain really quite nicely, sort of an S-shaped curve that almost built into the side of the hill. And it's actually part of the National Park Service, so there's an entire display on it. Oh, wow. Right underneath the bridge. You can go there and get your structural engineering education while you're up there hiking on the parkway. So it's another unique
I love
bridge.
The form follows function idea.
Yeah, it's a neat one. I think early 1980s it was built somewhere in that range.
Oh, nice. Let's see, I'm going to ask, this comes from Noel Castillo. He's in the city of Fontana, engineering manager. And he was asking, in layman's terms, what can your typical Caltrans bridge carry? And I actually was thinking about this a little bit. So
I'll let you answer that.
Okay. If you take a fully loaded big rig, 18-wheeler, those max out at about 80,000 pounds of what they can. Actually, that's fully loaded with the truck and the cargo. And if you take that as 6 feet wide, and usually a flatbed also peaks out at about 70 feet long. Is that right? And now I'm speaking.
Close enough.
40. Let's say 40 to 60 feet. So then you add in the length of the truck, and I think I had calculated this because I was curious about the question. It comes out to about 180 to 200 pounds a square foot, which is similar to the 2-foot surcharge that we use when we design retaining walls. So kind of aspect ratio wise, it makes sense. But also note that we don't design bridges for we design it for a typical truck load. It's not a full. It's a caravan of fully loaded 18-wheelers, because I think it would, especially for long span bridges, it probably wouldn't be economical to design that. So it's not 200 pounds across the whole bridge, but at least for that usual truck width and length, it'd be 200 pounds a square foot. So then this one comes from an elementary school in Irvine, California, and the question is...
The toughest question sometimes for
This
kids,
is going to be tough. And these aren't related to bridge design, so... Okay. Will anybody ever build a time machine or shrinking machine?
That's interesting questions. Shrinking machine. Well, I don't know. I think the second one, the first ones, they're both very interesting questions, I think, but the second one about shrinking is, I think, timely because of the miniaturization of everything, right? I mean, if you think about, to a certain extent, we're almost doing that now. There's things that you can put on, that we're talking outside of our area, but in microchips that have become, so small, and what you can store on these devices is just incredible. But you see some of that in structural engineering too, right? There's with people doing research and nanotechnology, the science of very small things. Approaching problems from the very small perspective. So it's not so much a shrinking machine, but maybe an appreciation for the importance of knowing the behavior of systems and materials from the very smallest of scales up to the very largest. And some of these 3D printers might be beneficial in some of
Right.
these, smaller
Right.
micro studies.
Oh, that is a great answer. And then the other one is, how do you think engineers can help stop global warming?
This is from the same.
Yes.
This is from the elementary
Yes.
school. Oh, that's a very very thoughtful question.
I think it's interesting how, unprompted, but some of those key words make their way into elementary
Sure.
school, and
Yeah.
kids are already starting to think about, how do these relate to us? So
Mhm.
how do these questions we're hearing about relate to us?
I would say probably the most, but this is, again, just my opinion, but I think something like this, from the engineering perspective, we have solutions to that. You have to overcome some sort of either whether it's a political issue or a policy issue. So a matter of educating a sufficient number of people who are making decisions
Mm-hmm.
to make changes to whatever that practice may be, whether it's building bridges with smaller carbon footprints or whatever it may be with regards to emissions.
Right.
I think, not to say that all the technology is there, but I think there's a lot of technology there that, if implemented, can help. And
Right.
there's maybe some inertia in some cases to implementation. But the examples of light bulbs, for example, right? Now all of a sudden we've gone from incandescents to the CFLs to, I just replaced a bunch of LEDs and they're in our house now, and they work quite well. And what's their impact on on global warming? Maybe not one bulb maybe doesn't do anything, but as a collection of bulbs around the world, it probably is quite impactful.
Right.
And I think educating consumers and educating politicians, convincing them of things that could be done efficiently, I think that's probably the biggest role. And in addition to the advances that we can do from a technological perspective on the engineering side. So I think those are two things that are possible.
Excellent. Well, I think that's everything I had. So I don't know if you have any final comments. I really appreciate you being available and open all these questions, and it was a really good discussion. So thank you. Oh, I know one last thing.
You didn't answer the question about your favorite bridge. You must have one.
Oh boy. Oh boy, you put me on the spot. Think about that.
I just had last summer. I was in Northern California, and I was traveling from Sacramento up into Sonoma and then down to the airport to pick up my wife before going away for a couple of days for the weekend. And between traversing from one side to the other, I had to cross over the Golden Gate Bridge, and I said, I'm going to get a sandwich and just kind of sit by the bridge.
Okay.
I said, this is a perfect spot, beautiful day. I've got an hour, and I got there thinking there would be no one else there at 6 or 7 p.m. And I walk out there, and there's this family there who brought a table and brought cheese and crackers and their food, and they were sitting there looking at the bridge. I thought it was quite neat. Do you have a family of Northern Californians out there enjoying the Golden Gate? So
that is nice. I'm thinking. Actually, my family and I recently came to Washington D.C. for vacation, and there's a canal that is it's downtown here. The Chesapeake and Ohio Canal near Georgetown. And it's just a very beautiful little area with the reason the bridge comes to mind. There's several little pedestrian bridges, more of an industrial look, smaller, but they're supported by rockery walls. And you've got the pedestrian trail below, and we were just skipping rocks, and it was a fun little memory. So I have this book here. I was wondering if you could autograph this book.
Oh, I'd be happy
it's
to.
Quite an honor for me. So
certainly.
Thank you.
Thanks, Judd. Any page in particular?
Oh no, anywhere. All right, thank you so much.
Thank you.
And I want to say thank you to everybody for listening in to this bridge edition of The Art of Engineering. You can find us online at www.taepodcast.com. And thank you again, Mervyn, for coming in. I really appreciate it.
Thank you, Ted.
Music for this podcast was made available under the Creative Commons license by Ben Sound. Music title Sunny at bensound.com.